Hello and welcome to the Waves and Radiation unit, and we're going to look at wave properties today in this slideshow. So what are wave properties? Well, wave properties are really things that all waves can do. And we're going to look at three of them: reflection, refraction and diffraction. Let's look at reflection first. Now, before we even do any of that, we need to just quickly mention ripple tanks. Now, ripple tanks are used to show wave properties very well. They're basically like shallow fish tanks with a little bit of water in them, and we have an oscillating paddle, as you can see here, and sometimes it's a paddle and sometimes it's just a bead, and basically that will oscillate the water, and that produces waves in the water. There's illumination up above that, and that casts a shadow, if you like, of the waves below on like a viewing screen, and you can actually watch the water waves. So there are two types of waves in the ripple tank. The first one, the one on the left, is a plane wave, which is like straight waves, and in this case it's going towards the right. The distance between two bands there is the wavelength. And circular waves, which are spreading out in all directions. These are caused by beads, usually, like a stone falling into, thrown into a lake or something. So reflection. So reflection is when waves bounce off things. And it's found that the only thing that changes is the direction. That doesn't change the wavelength, the speed, the frequency, any of the wave parameters, the velocity. They're all the same. The only thing that changes is the direction. And we've got a little diagram here, or as an animated GIF, which shows a wave coming in here and then going out. And if there's coming in, that's the incident wave, and going out, that's the reflected waves. And if you notice that the angles that they come in at and go out at are the same. And this brings us to the law of reflection, which basically it says that waves bounce off at the same angle they came in at. Sometimes we say the angle of incidence equals the angle of reflection. That's a more scientific way of putting it. So the incoming waves are called incident waves, and the incoming angle is called the angle of incidence, and reflected waves leave at the angle of reflection. So here we've got a barrier, and we've got an incident wave coming into it here. To keep track of the direction, we use a line at right angles to the barrier, and that's called the normal. Normal just means at right angles to a surface. It doesn't mean usual. And the reflected ray just comes off at the same angle that the incoming ray went in at. If I just highlight the angle that the incoming ray makes with the normal, that's called the angle of incidence, I, that equals the angle of reflection, R. So the angles are always measured from the ray to the actual normal itself. Remember, the ray is just really the arrow that shows you the direction that these waves are traveling in. So with curved reflectors, the only difference is that the waves just come in, but this time they're reflected to a focus. And that's how satellite dishes work. So you've got a wave that's spread out, it comes in, hits a curved reflector, and the waves are all brought to a focal point. So that's where you want to put your feed horn so that you can get a large signal. Okay, refraction is the second of our three waves properties. Refraction is really when you go from one type of material to another, or we say one medium to another. So there's some change in the material it's moving through, and it either speeds up or slows down. This can lead to a change in direction. Now what we're going to look at is water waves. Water waves slow down when they go from deep to shallow. So I've got a little demonstration here. So I've got waves, as you can see the three red lines are going from deep water into shallow water. And what happened there was that the wavelength decreased, and I hope you can see that the wave speed decreased as well. So going from deep to shallow, the waves slow down and the wavelength decreases. I expect you to be able to write that diagram. The frequency, however, is unchanged. Nothing changes the frequency. If I come in at an angle instead, I'm going from deep to shallow again, but this time you notice that the boundary is oblique, it's at an angle. Then basically the same thing happens, but we need to keep track of the angle this time. So we use the normal line to help us. The normal line's at right angles to the boundary, not at right angles to the wave, but at right angles to the boundary. And you can see that the waves have again decreased in their velocity and decreased in their wavelength. However, they have shifted their direction towards the normal. They're actually bending slightly towards the normal. They're not going in the same direction as before. Neither are they going along the normal, but they're going slightly towards the normal. And a simple ray diagram just shows this a little bit better. Again, I expect you to know that diagram. And of course, if you were going the other way, if you were going from shallow into deep, then the wavelength would increase, the velocity would increase, and you would bend away from the normal. But the deep to shallow one is the one that I need you to know for your exam. And what I've done here is that I've put the angle of incidence as an I, and the angle of, now careful, it's not the angle of reflection this time, it's the angle of refraction is an R. So this whole thing is called refraction. So refraction is really when they change their velocity. However, if you come in at an angle, you also change your direction, as you can see. And you'll see that all the time at a shoreline. You'll see that the waves, as they come in, change their direction as they get going from deep to shallow. Right, the last property is diffraction. So diffraction is when a wave spreads around an obstacle or through a gap. We can see here that we've got, this one was taken in Scotland, this picture, by the way. The waves are coming in through that gap there. And if you look at the direction of the waves, you'll see that they're actually spreading out in all directions. So if you've got a gap that's very wide compared to the wavelength, or alternatively a very short wavelength, then you can see that the waves do come through the gap and they do spread out slightly, but they still look pretty plain. So it's still plane waves, straight waves. So basically they're still quite straight, but they do spread out a little bit. On the other hand, if you look at the one below that, the waves are coming into a smaller gap, or alternatively, you might think of this as larger waves. And what they do is or larger wavelength waves. And what they do is that you can hope you can see they spread out much more. So they almost become semicircular. So you need to know that diagram there, the difference between a small gap and a large gap. Okay, so a large gap, they spread out a little bit. With a small gap, they spread out much more and become semicircular. Really, the important thing is that the size of the gap compared to the wavelength. Okay, so if the gap is smaller than the wavelength, they'll spread out almost semicircular. If the gap is larger than the wavelength, they spread out quite straightish. And the same thing happens for obstacles. So here we've got a wave coming around an obstacle, the bottom two diagrams, and you can see here that they both spread round. We've got a large wavelength and a short wavelength. The larger wavelength spreads more than the shorter wavelength. So shorter wavelengths don't spread particularly well around the obstacle. That's got a big application, and it's the radio reception problem. What you find is that people living in the shadow of hills, they experience problems when they're tuning into short wavelength TV. Now, it's not as much of a problem now with satellites and with broadband, etc. But in the past, it was a big problem, and the idea was that with the TVs, are short wavelength waves, and so they don't spread around the hills. So there's a shadow there, they just simply don't spread round down to that house at the bottom. Whereas the longer wavelength radio waves, they can spread out very easily around the hills, and so the house at the bottom actually got reception. So what should you know? You should know, first of all, how a ripple tank works, and you should know the law of reflection and the diagram for that. And by the way, you should know what a normal is. For refraction, you should know that refraction is when waves go from one medium to another and they change their velocity, their wavelength and direction, not their frequency. The one that I really need you to know for your exam is deep to shallow. I need you to know that they slow down, the wavelength gets smaller, they bend towards the normal and the diagram. You need to know these. You need to be able to just draw them. Diffraction is the last one, and diffraction is the spreading of a wave through a gap around an obstacle. The bigger the gap, bigger the wave, sorry, or the smaller the gap, the more the spreading is. You need to know the diagram for that and the radio reception problem. So there we go, that's us. That's all you need to know for this section of the course. So I want you to go through this now at your leisure. Click on the little blue buttons which take you to nice web demonstrations, read through the notes, and get in touch with me if you've got any problems. But hopefully that's helped a little bit for you. Okay, thank you very much.